Thank you everybody for joining. We're going to wait a couple of minutes just for everybody else to register and get through the into the attendees, and we'll start in about 1 to 2 minutes. So welcome to the Sustainable Composites Summit. My name is Tim Young from the National Composites Centre. This event is a collaborative event between two University of Bristol institutes, the Bristol Cabot Institute for the Environment and Bristol Composites Institute, as well as the National Composites Centre. We've got, for those of you who are just joining, welcome. For those of you who've been with us for the last few days, welcome back. We've got a 2-hour session with 4 speakers today. It's an exciting opportunity for questions at the end. So please use the Q&A at the end of every session. And you'll notice a hashtag for those of you who are so inclined at the bottom of the screen. Please use it, promote it. You'll see there's a lot of enthusiasm for getting composites sustainable and also generating some real outputs as a result of this. You will be able to upvote questions that you'd particularly like to see asked. And we are recording this session and live stream on YouTube. So recordings will be made available on the event page shortly after every session ends. So without further ado, I'd like to introduce the first speaker. This is Alan Paulson, who is the Cluster Lead for Sustainability and Advanced Materials at Vestas, and will be speaking to us about sustainable composite materials and the wind industry.
Yes, thanks. Do you hear me?
Yes, loud and clear.
Great, thanks. So yes, thanks, Tim. Thanks for the introduction. I will see if I can find the presentation. It's here. Share. Yes, thanks. As the introduction said, then my name is Alan Paulsen, and I'm working here in Vestas, currently sitting in Denmark, in our headquarters in Aarhus, and I'm going to introduce you to the Vestas work with sustainability and composites. Let me see how I move along. Yes. To introduce Vestas, we are approximately 26,000. 2 seconds here. 26,000 people worldwide. We are global, global presence. We have more than 45,000 wind turbines under service. Service is one of our big businesses. The other business is producing the wind turbines. We've produced more than 72,000 or more than 150 gigawatt of power. And we have wind turbines in more than 81 countries worldwide. Our revenue in 2019 were 12.2 billion euros. In the early 2020, we introduced a new sustainability strategy in Vestas. I am one of the main authors of this strategy, and also responsible for introduction and developing and implementation of this strategy. We are a team doing that, and I'm of course part of that. The two core elements in this strategy is that we want to be a carbon neutral company by 2030 without using carbon offsets. So that's actually meaning that we are going to reduce our own CO2 emissions by 100% in 2030, and then it's meaning that we're going to reduce our CO2 emissions in our supply chain by 45% per megawatt hour generated by 2030. That's one part of our sustainability strategy. The second one, and that's the one I'm going to talk most about today, that is about producing zero waste wind turbines by 2040. We have a couple of hot targets here, and that's the hub and blade to be 55% recyclable by 2030. And the big issue here is actually the blades made from composites. I mentioned these two parts of the strategy. We have four core areas, but the carbon neutral company and the zero waste wind turbines part are actually must-win battles for Vestas. So it's of high importance to us. Some of you might have seen these graphs before, but the thing is that the amount of composites from blades that reaches end of life is going to increase in the coming years. A wind turbine has a life expectancy of 20 years, and we have in more than 20 years installed wind turbines, and we install more and more each year. So the amount of composite waste is going to increase. If you take a look at this, then actually it will until 2028 we will actually have more waste from our production of blades. You can say that a rough estimate is that 30% of a blade mass is going to be wasted during production. The wind turbine manufacturer is not, or the wind industry is actually not that industry with most composite waste. That is the building and construction industry. However, these waste streams is really pretty or relatively fragmented and scattered all over. And then we have the electric and electronics, where the PCBs are made from composites, but these are heavily polluted by heavy metals and flame retardants and so on. Then we have some waste of composite waste from transportation and marine, and then we have wind. But wind is a relatively highly concentrated lump of composite we have in the blades. And as long as the wind industry also wants to be green and is a kind of a signature of a green industry, well, then we also need to take care and look into how do we recycle or get value out of the composite waste when it reaches end of life. And you will have seen, or if you have seen some of the news, you will have seen that the wind industry and the blade waste have been in the news quite recently. And this is just to show a few of the articles that are available. And you see it's both in Denmark. Yeah, it's a small country, but it's also in the UK, the US, and Germany and France. Actually, a wind turbine we claim it's 88% recyclable, and that's also true. Most of a wind turbine is made of steel and metal, so that's no problem about recycling with these materials. We've recycled metals for a couple of thousand years. But the thing is the polymers, it is the blades. 12%, approximately 12% of the mass of a wind turbine is the blades. They're very often made of fiberglass, a variety of resins. There can be wood in the blades as well, paint, fillers, and also carbon fiber. And it's really hard to get any value out of that. As you see, this is also to divide or to look into the materials in the blade. We do have the matrix. The resin matrix can be made from epoxy. Vestas blades are made from epoxy. Then you have polyurethane. Other OEMs are using polyurethanes, and then again others are using polyvinyl. No, it's polyesters. So there's a variety of matrix. There's also a variety of glass in the blades and qualities of glass. And then finally, Vestas are also using, and I think not only Vestas anymore, but most OEMs today are using carbon fiber in their blades. Vestas was the first OEM to introduce carbon fibers. We did that in 2001, which actually also means that it's relatively rare that you will see carbon fiber in used blades, because the lifetime of a blade is approximately 20 to 25 years. So we have to wait a few years before we start to see the carbon fiber showing up as a waste in the waste stream. Then you will have, as I mentioned before, most likely some wood. There is a risk that you will see polyvinyl chloride in it, PVC. That's an issue when you start to talk about recycling. And while we in the Vestas blade has a relatively high concentration of carbon fiber in the spar caps, then there is also a trend towards adding biaxial or hybrid carbon glass plies into the blades. And the issue here is that for some of the recycling technologies, you need to separate coal from glass. And for other recycling technologies, then there is a higher value of the pure carbon fiber and a less value of glass fiber. So it is an advantage to the blade technology, of course, because it makes strong blades. But on the other hand, there is an issue when we talk about recycling. The challenge of used composites, or the challenge of waste in general, is that in the whole value chain we do generate waste from when we acquire raw materials. Our suppliers, they also generate waste. The manufacturing part generates a lot of waste. I mentioned it previously. From blade production, you will see a relatively high amount of waste. Then we have the wind turbine. It will operate for 20 years, 25 years, and then it's going to be scrapped. Again, we'll get waste. And what we are actually working for in Vestas is to get rid of this. We want to get out of landfilling. We want to get out of incineration and get more value out of the waste fraction, or what is categorized as waste now, and want to enter a circular economy where we use the recycled materials in new materials. But the issue is, of course, that the driver for this is the business cases. And if you take a look at these different materials, you'll also see that there is a cost of recycling, and some of the materials are really hard to recycle. And that's a part of what we use, what we do in Vestas. That is that we try to catalyze the value streams around recycling, around the recycled products. And we're also trying to catalyze the development of technologies that is developing recycle, or catalyze the development of recycling technologies. Finally, we're actually also working on development together with partners on new resins, for instance, that can be dissolved at end of life, for instance, so that we can separate the resin from the fibers. It sounds easy, but it isn't necessarily that easy. You will see today that a lot of used blades are used for a variety of purposes, and in a lot of projects you will see that somebody used them for science, for instance. There's also that's actually in Denmark, where there's a part of a blade that is being used as a bicycle shed. It's been used for furnitures, playgrounds, and other things. This is yeah, I think it's there's some people who have some great fantasy here, but to my opinion, this is not the way we need to go if we talk about recycling or reuse of blades, simply because people, they will know that this is waste. And there was a survey made in Denmark, and they made a bridge out of 2 blades, and people, they were very well aware that this was industry waste, and the industry didn't know what to do about it, so they started to put it out in the surroundings, and they really didn't like that. Also, then the blades are in a variety of shapes and sizes, so it's really hard to industrialize this kind of recycling of old blades, and so you need to figure out something else. If you take a look at the waste treatment hierarchy, then the bottom, that's the disposal. That's where we don't want to be. We want to move up the life cycle, or the waste treatment hierarchy. Sorry. We are looking into recovery. Of course, that is where we can add the used blades. We can shred them and add them to a cement kiln. I'll get into that afterwards. Then there are some recycling that can, for instance, be pyrolysis or chemical recycling. There's also repurpose and reuse. That is where you use the blades again. There's actually quite a large market for second-hand blades and second-hand wind turbines. So we refurbish the blades and sell them again. But that's only I mean, that's mostly smaller blades. As the wind turbines grow larger and larger, then there'll be a transport issue, because then it'll be too expensive to transport them compared to just getting new blades. Some of the processes that are available right now for recycling of composites, that is the cement kiln, as I mentioned before. And I think that this is most likely one of the best ways of getting rid of old blades, because if you say that a blade is 50-50 glass and resin, then the glass is substituting sand that you are adding to the cement kiln anyway. That's substituting to the clinker, and the resin fraction is substituting coal that you use to heat up the chemical process. So both components of the composite is used here. There is, of course, an issue with carbon fiber, because even though the temperature in a cement kiln is between 1,500 to 2,000 degrees Celsius, then you will have small particles of carbon fibers that is not incinerated in this process, and they will leave as dust and unhealthy fractions from the process. So you need to separate that out of the blades. Normally, that is not a big issue. But before you added it to a cement kiln, you need to do some mechanical recycling. You need to grind it into a powder. Here, this powder can also be re-glued together to new shapes, and some companies are actually doing that. But that's also a kind of storing the composites. One day, these furnitures or materials or construction materials you use in that way will be needed to recycled. Then you have the fluidized bed technology. Some universities are looking into that. There's solvolysis. That's actually promising, especially for the resins that can be dismantled afterwards. And then we have the pyrolysis. That is a well-established technology and very much used for especially the carbon fibers, because there is a market for carbon fibers that has undergone pyrolysis. The thing is here that the fibers, they are losing some of their strength when they are being solvolized or pyrolyzed or going into a fluidized bed. And also we're not talking about continuous fiber anymore. They're chopped into pieces, which meaning that we cannot use them in a wind turbine anymore. The thing is also that when it loses strength, let's play with the idea that you could actually make continuous fibers, and you could actually resize the fibers, the glass fibers. But you'll have the issue about the lost strength. Then this will mean that we need to build heavier blades, and heavier blades will entail that we actually are going to increase the amount of steel in the tower, the amount of concrete in the foundation, and the whole construction needs to be heavier, and that will also have a high impact on the sustainability level. One of the issues here is also the energy that you need to use for recycling. If you take a look at the left side here, you have the energy needed for produce a kilo of carbon fiber, and you have the energy needed to use to produce a kilo of glass fiber. Then if you take a look, this is numbers that I found in a variety of papers. So that's why there is it's between 21 megajoule per kilo and 91 megajoule per kilo, is because I found both or values in between these two extremities in different papers. But what you will see is that it's actually more energy demanding to do solvolysis or fluidized bed or pyrolysis recovery of the fibers compared to just production of a pure virgin glass fiber. And that is really one of the issues. We need to drive this energy consumption down, and of course the energy needs to come from renewables. So these are some of the issues. If you take a look over here, you will actually also see that some of the most promising technologies with regards to energy consumption, high voltage pulse fragmentation and microwave, they still need a lot of technology development before they can actually be used in the industry. Then there is also alternative materials. There is thermoplastic blades, thermoplastics. One of the issues here is that I still need to see that you can get a pure and continuous fiber out from the blades afterwards, and that you can get a higher value out of the resin when it's degraded again after use. Then you also have flax fibers. Here there is potentially an issue with the volume of the fibers. Then there is the wooden blades. We've done that before in Vestas. We have had wooden blades previously. That could be promising. With wooden blades, there's a good strength in wood, and technologies are also available to align the fibers in the wood. And then there is of course also recyclable epoxies and thermoplastics again, and also other technologies for blades that have a higher degree of sustainability in them. And that's of course the way we are. Of course, some of the areas that we are interested in here in Vestas. How do we make our monolithic blades more sustainable? So yes, this was everything from me. I want to say thanks for your attention, and I hope you have a few questions.
Brilliant. Thank you, Alan. That was absolutely brilliant. So just while we wait for the questions to do, there's a slight lag on some of them. I was quite interested in your estimations on the composite waste stream, and quite encouraged also by the vision from Vestas on the circular economy. Do you have any shared challenges and priorities that therefore exist between the different sectors that perhaps academia and RTOs could help with?
I think we are involved, but we're not the only OEM that are involved in technology development. For instance, we have been working with several universities of development of new resins that can be degraded at end of life. Mm-hmm. And that is actually very adjacent to our industry, because it's not our business really to make new resins, but it is so important to us that we would like to test and be a part of that development. We've been working in a project called Dreamwind together with Olean Epoxy on development of new resins, for instance. So it is of great interest to us. We've also been working with several universities and technology developers within development of recycling technologies, but we are still waiting for technologies that are industrial scalable and where it is economically feasible. And that's also the same with the resin. If the cost is too high, then we have a problem, because then our customers and our customers, that's actually you and me, are not willing to pay that extra price for our electricity. So that is what we're looking into. So we need to drive the cost down of these, and that's actually also that's why we are very active in this area, and that's also why we often or now and then collaborate with our competitors, other big OEMs, to reduce the cost of recycling technologies, or to reduce the cost of resin technologies. Because we know we cannot drive that alone. We need to have a very large scale before it's driven down in price.
So we've seen two questions come through that kind of touch a little bit about capacity. One's in the context of where in the manufacturing process of the blade is actually the most waste generated. And then the second one's a bit about kind of, I'll ask that second. Let's go for the first.
Yeah, for instance, when we do kitting, there we will see some waste. How do we exploit the plies in the best fashion? We will have cutoffs of dry ply, of pre-preg plies. That's where we will have some cutoff. We will have cutoffs from protrusions and so on, and that's where we will see waste. Then there's also waste from the infusion, of course. That's plastics, hoses, valves, and so on. But that's a minor part compared to the cutoffs from the plies. I think if you look into the literature, it says there's approximately 30% by mass is going to get waste in the blade production.
Thank you. So the second one, I'm not sure how to ask this one quickly. So if Franran can think about how to write it, we'd love to ask that one later. But it's really around wind turbine size evolution and how often or how long does it take to evolve between an older wind turbine with lower capacity to a new wind turbine with larger capacity?
You can take a look at the design. It actually have a lifespan of, let's say, 10 years. Some of the designs we sell now, they have been designed 10 years ago. So there is quite a long lifetime for some of the products that we have. That also means that's why we need to look into 2040, because the things that we design now will have a long, or some of them, the most popular products, will have a long time on the shelf in Vestas. So if we, for instance, decide today that we would like to introduce a new resin or a new fiber technology, then it will take some years before we actually introduce it to our new products, because we need to test it, we need to be sure that it holds, we need to have it approved by DNV, GL, and so on, and then we will have that product on the shelf for some years afterwards.
So talking about kind of the longevity then, how would you, or how is the residual life assessed then when selling blades for a second life?
It has a design lifetime, and then we are actually making the back calculation. So we have the log on the wind turbine, and then we know how much it has been curtailed and how much it has been operating at its highest stress level. And then we can make the back calculation of the residual life in the blades, but also in the tower. Sometimes it's a tower who doesn't have any residual life in it anymore.
Okay, thank you. So there's quite a few questions, all interested in the life of blades, and just to touch on the second part of the question that's related is, what is the most? This is from Mark Lidgett. What is the most common reason for decommissioning a wind turbine blade, or wind turbine? Sorry.
That's simply the business case. There's two reasons why you decommission a wind turbine. The first one is that it's simply too old. I mean, that's it has reached its end of life. The second one is that perhaps you have a wind turbine that is 12 years old, but and you have a site for it, But if you buy or purchase a new, more efficient wind turbine, then you have a better business case. And then you just swap, let's say, two 2 megawatt wind turbines with 1 4 megawatt new, more efficient wind turbine. So there's several reasons why you purchase new wind turbines.
Thank you. So there's a few questions all focused around natural fibers from a number of people. I'm going to try and lump them, but really around how feasible is it to be using natural fiber, and how would you cope with the variability?
I think, of course, the variability, you can just cope with that in adding more fibers. Then that's one part of it. But then you'll have a heavier blade, and there's also the volume of the natural fibers is a bit larger. So that's a disadvantage to the blade. And the price tags we've been studying at natural fibers is also more or less twice the price as glass fiber. The thing is that glass fiber is really cheap to make, so it's a fierce competition when you look at glass fiber. I'm very well aware of that, but that's how it is. And as long as our customers, they won't put an extra price or onto sustainability, then we also need to take that into our consideration if you want to stay in the business. But of course, we are working with both our supply chain and our customers to try to drive these prices down on alternative materials. And we are also working with our customers to somehow work with sustainability and the added price and the added cost we're working on that with our customers. Of course, they are also very keen on being more sustainable in the wind industry, of course.
Okay, so a couple of things you've touched on today, and also in some of the answers, is reducing the cost of some of the alternatives and making recycling more economically viable. There's a question here around, is there any research with Vestas to increase the life of the wind turbine blades? 20 to 25 years was mentioned, which might be an alternative to offset some of the cost.
I think that I'm not an expert on that part, but I think if you want to design a blade for longer lifetime, then it's most likely also going to gain in weight. So you have some trade-offs there. Then there is also the thing that is that wind turbine compliant with the grids for such a long time. That's actually also what we see. Then old wind turbines, they're not grid compliant anymore. So even though that we could make a wind turbine that had a lifetime that could last for 50 years, there might be some technology development that you need to take it down anyways.
Okay, so just sticking with the longevity point, with wind turbines, this is a question from Henry Sarrell Coke. With wind turbines being used for some time, has their life cycle matched your original FEA assumptions? Specifically, if they degrade more quickly, would it be more efficient to use more carbon than glass?
No, they have actually not. They've not completely been living up to our FEA. They've had a longer lifetime than we expected. So that's good. They're designed too robust. No, but that's actually good. It's a good product. So they have a longer lifetime than you should expect from the very beginning. There's no worries there at all.
So just one last question then. Just there's a few of these left, but we're nearly at time, and it's really around health monitoring techniques. There's a few of them, so I'll put them into one. But have you been investigating, and how do you monitor the health of your turbine blades? So
monitor the health. I mean, that monitoring of health can be a variety of things. Of course, we do have sensors in a blade, so we can always measure the deflection. We use that for the control of the wind turbine. Then we are also inspecting the blades, for instance, for wear and tear, especially on the leading edge. So that's more or less how we monitor. And then, of course, we have all data on on the forces that the blades have been seeing through their lifetime. That's also how we managed to calculate the residual lifetime in a blade. So we have these. We don't have special sensors or so that measure the blades and the condition of the blade as such. We have a lot of other indicators. Yes.
Oh, thank you very much. Thank you very much for such an interesting talk. And we understand you're not able to stay for the whole thing.
No, I'm sorry for that.
That's no problem at all. Thank you so much for quite an engaging and insightful insight into what's going on in Vestas.
You're welcome.
So let me just switch over to. So if I can now introduce our next speaker, this is Lucy Eggleston. She is the Sustainability Research Engineer at the National Composites Centre and Technical Lead of the Rediscover programme. She will be talking on the National Composites Centre, particularly the Sustainable Composite Partnership and Rediscover Next Steps.
Hi everyone, thanks very much for that, Tim. So as Tim said, my name is Lucy Everson. I'm a Sustainability Research Engineer at the National Composites Centre. And today I'm going to be talking a bit about the Sustainable Composites Partnership that I think Tim would have introduced you to yesterday if you were able to catch his talk, and kind of take you through the journey of how we got to where we did today. I know a number of the people who are on the call today were part of Rediscover in some way. So we've got a bit of a background about that and some more about what the NCC has been doing aside of that to kind of increase our sustainability capability and really kind of enforce our credibility in the area. So I'm just going to try and share my screen with you all. So hopefully this should work. Is that working?
Yes, all good, thank you.
Awesome, thank you very much, Tim. So yeah, as I said, the Sustainable Composites Partnership, I thought we'd just start with a bit of a very brief introduction to that before I carry on, just in case anyone missed Tim Young's speech yesterday. So the Sustainable Composites Partnership is a partnership between industry, academia and government, bringing together the UK's composites expertise to quickly turn research breakthroughs into industrial applications. So what we mean by that is we are a network of organisations right across the supply chain that have the ability and drive to cause a step change in the way the world thinks about composites and sustainability. We're working with academia to pull through new promising innovative technologies, but at the same time, we're also working with industry to determine what their requirements are and where they really need us to go. So from my perspective, listening to some of the talks this week has been really, really insightful. And it's been great to be asked to be a part of that. So thank you very much. So as I said, what I thought we'd do today is go through a bit of a journey of the Sustainable Composites Partnership through the eyes of the NCC. So obviously it is a partnership between the NCC and CPI, but I work at the NCC and this is kind of my take on it. So the drive for sustainability at the NCC began approximately 5 years ago, I would say, and when the proposal for a new sustainability team was conceived. About 4 years ago, we had a mixed team formed called Multi-Materials and Sustainability. So the Multi-Materials was focusing on more ceramic matrix composites and sustainability, obviously sustainability. And at the time, neither team had enough interest to warrant being an entity in their own right. So this kind of joined up approach was formed. I joined just about 3 years ago now. I think we're coming up on my 3-year anniversary. Into this team, and at the time we were kind of investigating the possibility of these alternative feeds, like these natural fibres and things, and playing around with flax and jute and bio-based resins. We were learning more about life cycle assessment, about the circular economy, and also about our own impacts and how we could kind of minimise that. So about 2 years ago now, the proposal for a large transformational project focusing on circular economy for the composites industry was written. This turned into what is now known as Rediscover. This is kind of the first key point of my presentation today. By no means was it the start of our sustainability journey, but it was where we started to see kind of a greater level of engagement across industry, and it was well timed with a lot of the public learning and perception that was going on at the time with sort of climate change strikes and things like that. So if this will work, yes. So Rediscover, for anyone who wasn't involved, I thought I'd just spend a couple of minutes explaining Rediscover, what it was, what we did, and where we are today as a result of it, because it was a big part in helping to inform the Sustainable Composites Partnership. So the aim of Rediscover was to transform the UK's world-leading composites end-of-life academic and commercial capabilities into a fully functioning and interconnected supply chain, which is a bit of a mouthful, but essentially what we mean by that is there were these real pockets of excellence in the UK, there always have been. So whether that be with the University of Nottingham's Composite Research Centre, or ELG Recycled Carbon Fibres, the first continuous recyclers of carbon fibre composites in the world. There are these little pockets of excellence, but it was a bit disjointed, and we felt that a joined up approach and getting everyone talking to each other would be really beneficial for industry as a whole. So Rediscover as a large transformational project was a cross-catapult effort between 6 of the 7 catapult centres. And we worked together to essentially determine what the opportunity was, build a network of people, and then figure out what we could do with this network of people moving forwards. This little graphic that you can see at the bottom of the screen here kind of takes you through our journey. So at the very beginning of the project, we researched roadmaps and whatever we could get our hands on, basically, whether that be through Google or through contacts within industry, whatever we could do. And then we analysed those for any common themes or common opportunities that seem to be coming up time and time again, whether that be in a particular industry or across a number of industries. We looked for all of those sorts of trends. After that, we reached out to industry for their feedback, and we spent a lot of time talking to some really interesting people who are very, very passionate about sustainability within their fields. And we basically just asked them for their feedback on what we'd found. In some cases, we were pretty spot on. In other cases, we'd completely missed something huge for them. And so that was a really great opportunity to really get a well-rounded view of industry. From all of that feedback, we then worked as a team to create a suite of 24 different project ideas that we felt that, if addressed successfully and at the right scale, could really begin to solve those issues faced by composites at end of life. With those 24 projects, we hosted a large-scale event at the NCC that I know a lot of you were at. We had about just over 100, I think, representatives from industry, and it was a really kind of inspiring day, because there were all of these people in the same room from different sectors and different areas of the supply chain, but all with this same common goal. So it was a great day to be a part of, and we got a lot of very, very valuable information out of that. I think we had about 2,000 post-it notes, which took a lot of analysis, but following some pretty considerable time, we identified that 13 of those 24 projects were in particular need for immediate progression. And that led us to hold a series of what we called project development sessions, where we worked with industry right across the UK to kind of flesh out what a project in that area would look like. So what would the rough work breakdown structure be? What would the scope be? What were the requirements? What was the rough scale of the project in terms of cost and also time? And that left us with a number of kind of semi-scoped projects, an amazing network of which you can see the participants on the screen there. And also a real idea of kind of where the gaps were and what needed doing. But of course, then something needed to be done with them. And I'll come back to that in a minute. But at the same time as Rediscover, over the past few years, we've also been working at the NCC to develop our own internal capability. And a lot of that has been around sort of modelling the impact of the processes that we use. We've learned a lot about value stream mapping. We've done some investigation into sustainable materials. And we've also been learning about the circular economy and what circular economy thinking is and how it can be applied to the composites industry. So we undertook all of this with the aim of increasing our ability to deliver impactful sustainable composites research and development for industry and academia. And the real key there was that it's both industry and academia. So we do CR&D or collaborative research and development or commercial work for industry, but we also work with academia to pull through their technologies. And one of my later slides is about one of our pull-through projects that was particularly focused on sustainability. So the pictures here you can see, we've got this one here was a sustainable noise barrier made from recycled thermoplastic pellets and a polyurethane foam with flax skins. We've also looked at using Recyclate with Shell to mock up some of their pricing monoliths. We've looked at a number of different pieces of software, such as and become proficient in a number of pieces of software, such as SimmerPro and Garby for LCA, and also looked internally within ourselves as well and tried to quantify our environmental impact and what we think our vision for circular economy for composites is. So with that, I'll take us on to one of the projects that we have been working with academia particularly closely on. So this project here, this slide is about a project called Dismantleable Joints. Dismantleable Joints was part of the NCC's technology pull-through program last year and was done in collaboration with Oxford Brookes University. Now's probably not the time to talk to you too much about the technology pull-through, but it is a program that we have running at the NCC every year where we identify promising innovative technologies within academia and work with them to pull them through to be more industry ready and increase that type of technology.
Hello everybody, so unfortunately we seem to have a slight technical hitch right now. Lucy, are you back on?
I am, is that better?
That is much better, yes. We lost you for a second. That's not a problem, you're just saving yourself a minute on some of the questions.
My internet is pretty shocking.
That's fine. Do you want to start again and I'll turn my video off?
Yeah, sure thing. Let me just... This one. Okay, is that back working again? Yeah.
Yes, absolutely brilliant.
Yes.
Thank you.
Awesome. Thank you very much. Sorry about that. I've got a bit rubbish internet. So back to the project Dismantleable Joints. I think I probably got through a bit of it. So a quick summary. So we were looking at different additives that could be included in adhesives and triggered by specific external stimuli to cause disbond, leading to the possibility of innovation in repair and modifications, as well as more efficient disassembly at end of life. There is a video here that hopefully you can see on the right hand side, and that is using a heat gun to activate expandable graphite within a structural adhesive adhered joint. And that sort of happens in the rounds of about 30 seconds to a minute, but we investigated other heat sources as well that could do it much quicker. So alongside investigating those different heat sources, we tested the bond strength of the joints that we'd created, as well as investigated the usability of the adhesive once they'd been combined with the additives, so that we really got an idea of kind of how usable are these and how easy would they be to just slot into everyday manufacture. Alongside that, we assessed the durability of the joints, and once we had all of that information, we used it in combination to create a technology demonstration. And the reason I highlighted this project in particular, and this isn't the only one, there are a number, But the reason I've highlighted this one in particular is because it generated a lot of interest across industry. We created a short video about it that you can see on our LinkedIn or our Facebook page or our website. And it caught the eyes of The Economist, actually, which was really cool. I got interviewed by The Economist for that, which was definitely something I never thought would happen. But it really enhanced, what was really great about this one was that it just proved our credibility, and it proved what we've been working to do for a long time. And it was also the bonus of being a really, really interesting project. So next on our journey is the Sustainable Composites Initiative. It's kind of where we are today. And I just wanted to spend a minute or so talking about the mission of the Sustainable Composites Initiative and kind of what we're doing. And then following on in the next few slides, I'll tell you about a couple of the projects that we've kickstarted already and are underway. And then spend a little bit of time talking about the future opportunities that we have in the space and how we would love to get some of you on board with the initiative and involved in some of the projects. So first of all, the mission for the Sustainable Composites Initiative is to ensure that the next generation of composite materials, designs and products support net zero ambition, securing the UK's position as a world leader in sustainable composites. And we're doing that through a number of different routes. We're developing our internal capability through Kickstart projects, and I'll tell you about two in a minute. We're also looking to create tool sets for industry to use so that they can develop sustainably as well. We're coordinating national partnerships and we're enhancing our network that we've already established quite well. And we're also looking to accelerate funding opportunities, whether that be for academia, for industry, or for a combination of the two. And the underlying theme behind all of this is that we want to be really clear and disseminate the message. Hopefully you will have seen our animation and maybe our new website, but if you haven't, there's a link to it at the end of my presentation. I would definitely recommend going and having a look. Our animation in particular is something that we're very proud of. It's a bit of an introduction to the topic and what we're looking to do. So on that note, I will spend a second talking about one of our Kickstart projects. We've coined it Steam to Value Stream, and it's looking to investigate and demonstrate methods for improving the maturity of fibre and matrix reclamation. It's kind of a four-step approach, the project, the first of which is we're looking to industry to identify the key waste streams. And we've highlighted, as was reinforced by Alan's presentation earlier, we've highlighted both the wind energy industry and the aerospace industry. So two very different material types, two different problems, but both need solving. So we're looking to those to start with. The second step of the project will be to reclaim the material, and we are investigating a novel steam-based process, working with an SME based up in the north, who have a promising technology that hasn't yet been proven out. So we're looking to assess the feasibility of that, and then using that in combination with the University of Bristol's HyperDiff process. So we'll look to reclaim some fibres using the steam process and then realign them using HyperDiff to create a high performance semi-preg tape that will then be used in stage 4 of creating new parts. The key drivers behind this project were that, as we know, there are increasing volumes of composite waste entering the waste stream, and kind of limited end-of-life solutions at current. Couple this with the increasing legislation and requirements of regulation, and you've got a real opportunity for value gain that we're keen to capitalise on and help the industry to capitalise on too. So we're hoping that the outcome of this project is that we'll better understand the environmental impact of recycling at current and also recycling of the potential for recycling in the future. So I know a couple of people have asked questions or have spoken about when does it become economically viable to recycle some materials, in particular glass composites, and we're looking to really understand that in this project. We'll also be interrogating and articulating the business case for recycling and creating demonstrators using that recycler in whatever format we can get it into. So this is a really, really exciting project and combats a number of issues for a number of different industries. So if anyone's has particular interest in this one, then we'd be really, really happy to hear from you. And yeah, definitely get in contact on that one. The next project that I wanted to talk to you about is our Bio Bolster project. And this is the second of the Kickstart projects within the Sustainable Composites Partnership. And this is looking at the other end of it. So in this project, we're looking at diversifying feedstock and that beginning of life and lower impact materials. And our aim is to validate and showcase the use of bio-based resins for high volume and high value manufacture. The key drivers behind this are we're seeing an increased appetite from industry for these sorts of materials, but there's sometimes some hesitation because there's a bit of an unknown. So we want to kind of de-risk these materials and diversify the feedstock options that there are available. Within the project, we'll be identifying the current state of the art, so we know where we are currently. We'll then be developing a bio-based resin system and using that resin system to manufacture bio-based demonstrators. Finally, we'll be keen to, as is the theme with the Sustainable Composites Partnership, disseminate and exploit. And then the outcome will hopefully be, or the outcome will be that we understand the environmental impact of using bioresins. We'll have a demonstrator using those resins as well, and we'll have built the business case. A theme alongside this is kind of that identification of future opportunities. So again, if anyone's particularly interested in this one, we'd be really interested to hear from you. So I've got one slide left, and that's about our future opportunities. So as I've said, a really big part of the Sustainable Composites Partnership is the network and bringing industry along on the journey. So we will be looking through a number of different routes for ways that we can engage with you and increase our understanding as well as industries. So we'll be looking to support innovative projects. We're still working out how we can do this at the moment, but we've got a number of different ideas up our sleeve. So if anyone has anything in particular, then we'd be really keen to hear from you. We're also looking to offer industrial supervisors to students at universities and provide dissertation titles where that's appropriate. Something that's particularly pertinent to the current time is we're looking to build collaborative R&D consortia to access external government, external funding from different sources. The reason I say that's particularly pertinent at the moment is because there's a number of funding calls we have our eyes on at the moment, and we'll be sending an email out in the next couple of days to our Rediscover plus, therefore the Sustainable Composites Partnership network. So if you're not a part of that, then definitely get on our website and have a look. And finally, we want to provide STEM opportunities to school-age children and communities, whether that be local or national, so that we can really inspire the next generation of sustainability engineers. So I've got our email address and our website down at the bottom there. But with that, I will end my presentation and say thank you for your time and ask if you have any questions.
Thank you, Lucy. So again, whilst we wait for some of the questions and answers to come through, for those of you who've asked questions in the last session, some of those have been technically dismissed. What that actually means is we're parking them for the later panel discussion because they're nicely answerable by a number of the panelists. But Lucy, back to you. I'm actually going to use Mike Hinton's question from yesterday, which was quite a good challenging one that had us all thinking, and one that should therefore be shared. If you had a bag of money to spend, what would you spend it on?
Does it have to be to do with composite?
Yes.
Okay. No, jokes aside. That's a really good question. I think there are a number of things I'd spend it on. I think one of the most relevant topics at the moment is recycling and end of life. But if I had an infinite bag of money, I'd want to take a real systems level approach to transforming the industry. I think linking up the supply chain is the first step, but in order to really make the industry resource efficient and work towards that goal of net zero impact, I think it's going to take a whole system level change approach. So I'd go about facilitating that some way. I think there'd be a lot of networking, a lot of education, and some technology development as well.
Oh, thank you. I've got another one, Koo. So is there any funding for early career researcher in sustainability aspects of composites?
That's a really good question. So I would say what we're looking to do at the moment is support that network. I don't quite have the ins and outs of how we can do that at the moment, but I would say definitely get in touch and we can have a chat about that and we can see what the options are. And I'm very happy to talk about kind of my experience and how I've got to where I am today. And if that would be any help at all, then I'm very open to that.
Thank you, Lucy. So does the Sustainable Composites Network include any stakeholders from the defence sector, e.g. Ministry of Defence or DSDL?
The Sustainable Composites Network does include a couple of people from the defence sector, neither of the two that have been used as examples there at the moment. Defence is an interesting one. We're definitely seeing interest though from a number of different parties. Sometimes you have to think a little bit laterally about where that interest is coming from, just because they've got slightly different drivers. But I would say that in particular, the DSTL structure of support and funding at the moment is kind of favourable in terms of some sustainability approaches. So we're definitely interested in further exploring that relationship.
And in the interest of time, I'm going to ask one more question that's just come through. So for the development of the bio-based resin, do you collaborate with countries outside the UK? And how do your properties compare to thermoset or thermoplastics?
That's another really good question. In terms of collaboration with countries outside of the UK, we're always interested to hear how we can further expand our network. As a catapult, quite often we begin with the UK as we're funded by UK government in part, but there are such pools of knowledge and expertise from wider afield, and it's always really interesting to us to hear of new ideas. The second part about properties.
Yeah, how do the properties compare with thermoset or thermoplastic resins?
Again, it kind of depends on what the bio-based alternative is. So you can get, you have a group of materials called bioplastics, such as bio-PET or biopolyethylene, and they're actually chemically identical to their petroleum-derived counterparts. They just use a different feedstock as a source. So they use something like glucose from sugarcane bagasse or something like that. When you start looking at thermosets and you look at epoxidized naturally occurring oils like sunflower oil or soybean oil, the variation in properties is huge, as is the variation in properties of thermoset materials. So what's really key there is to set out your boundaries of what your performance requirements are and look for a material that would suit that. What's really interesting about some of these natural materials though is that sometimes they have inherent advantages that you wouldn't get within petroleum derived ones. So for example, inherent fire retardancy or with natural fibers, things like vibration damping and things. So it's just about knowing what your requirements are and understanding the limits of your materials.
Thank you very much, Lucy. That's a really engaging talk, and it's great to hear more about what's going on. So we'll park some of the rest of the questions till later. And I'd like to introduce our next speaker. This is Kevin Lindsay, who's the Managing Director of FAR Composites. And Kevin will be speaking to us about sustainability of transportation in a circular world. Where do composites fit in? So over to you, Kevin.
Thanks, Tim. Hopefully that's sharing okay now. So we've been talking a lot about different areas of sustainability, different applications, which is most of this session. But we'd like to talk today a bit more about how we could use some of these materials in the transportation industry. So FAR UK has been working in composites and the automotive area for a number of years. And personally, it's something which I've been working in for sort of many more years than that. So we've got a bit of a background in this. And rather than focusing on some of the things which are happening today, I think the byline of the sort of speaker requirements on this was to understand what we need to do to take us towards net zero. And some of those ideas is what I'd like to explore today. I always like a good quote, and this is quite a well-used one, really. For a complex challenge, there's quite often a simple solution, which is sometimes quite often wrong. And if you need to have a complex challenge, you need a complex solution that quite often takes time. And we'll be talking a little bit about that as we go through as well. But what I'd like to do is, before we go on to talk about some of the sustainable composites, it's probably worth coming back and reflecting of why we're thinking about using composites as a whole, and why we want to try and get maybe increase some of the composites as we go through. Over the course of this conference, there's been a number of people been talking about life cycle analysis, and what we have here is sorry, I just need to show that. And what we have here is a life cycle analysis of a typical set of vehicles. In green, we're showing the amount of CO2 equivalent emissions from the materials and manufacturing, and the blue represents the in-use phase, where we are having CO2 emissions, whether that's directly from the tailpipe or related to the fuel being taken out of the ground in whatever form that is. So the underlying premise is, if we reduce the weight, we reduce the in-use emissions, and overall we get a better environmental analysis. We're all aware that as there's an increased use of electric vehicles, and there's many OEMs many vehicle manufacturers who are pushing the use of electric vehicles. What we're trying to do there is to say, well, actually, overall, we may be able to reduce CO2 emissions even more, but we can offset that. So some of that is offset by the increase in the energy required to make the materials and also to make the vehicles. So we have a fairly complex solution system here, but what we're trying to do is to, again, reduce the amount of CO2 which we're emitting over the life cycle of the vehicle. And that's what's been driving, I suppose, the use of lightweight materials over the last 20, 30 years. And it's in that context which I want to try and talk about how do we start making some of these things sustainable. Because we're talking about reducing rather than towards net zero. And that's a distinction which I would like to pick up. There's a few things which I want to talk about the life cycle analysis as a whole. And we've already mentioned that weight saving can lead to energy saving. Going electric will help, but only if it's fully renewable, and it isn't the answer to many of the problems. Although light weighting itself through the use of composites may actually also have some secondary benefits by reducing the amount of batteries we need, whether that's through acceleration or range. But so overall, we can have something which gives us maybe a better solution, but all of this does come back to what we see in the life cycle analysis. Again and again, we come back to all of these things must add together to make sure we have an overall better environmental position. If we're talking about cars in any way, shape or form, yeah, I think it's contractual, but we must mention the Automotive Council and their roadmaps. And for those who don't know, the UK Automotive Council, along with other trade and industry bodies, have put together sort of a vision of the future. And these things cover everything from batteries through to materials. But the one I want to talk about here is the passenger car. And in particular, there's a couple of things I would just like to highlight. The first one, when we're talking about legislation, at the moment, we've got the emissions from vehicles is measured as tailpipe emissions. So we're emitting carbon dioxide from the vehicles into the environment, And what we're measuring is what's coming out of the tailpipe, which works very well for an internal combustion engine. But when we go to electric vehicles, which effectively have zero tailpipe emissions, maybe that will start to distort the real underlying picture of what's going on if we see the expected increase in electric vehicles. So what we're suggesting here is, over time, not only are we looking at tailpipe emissions, but as it says here, a first stage to well-to-wheel emissions. And then, as suggested here, maybe going beyond well-to-wheel emissions, there is a requirement where we'll look at total life cycle emissions and total life cycle accounting for a whole range, not just for the fuel which is used, but across the whole vehicle. And as we look forward towards sort of net zero and look forward to the future, this is the thing which is maybe start to drive some of the thinking in the automotive and in the wider transportation area. So it is not just about turning electric, it's starting towards how do we look about the whole life cycle. And again, life cycle analysis will be an important part of that. And I'm sure there'll be many debates of how we handle recycling credits, whether that's for composites or aluminium or whatever that is. And I'm sure we can all look forward to many years of those debates. From a far UK point of view, we've been trying to understand what sort of things are going to be required in the future. And first, I need to thank Mark Lidgett, my colleague, for putting this infographic together. But we see it sort of breaking down into three areas. There's this idea of led by analysis, circular in nature, and made by robots. And when we say working backwards from there, made by robots isn't really just about automating what we have. It's how do we change things to make things which are robotic manufactured. In addition to that, what does circular in nature mean? I'm going to, in the next slide, talk a little bit around the design for inner loops and how those things are implemented and what sort of things we could get out of that. But underlying that is this idea of we are led by analysis. And again, we'll pick some of these things up as we go through a couple of examples. This is probably a fairly famous butterfly diagram from the Ellen MacArthur Foundation. I didn't realize this caused so much talk in the academic circles, but I'm going to go with it because I think it's a nice picture and it does illustrate a couple of points. I mentioned on the last slide that what we're looking about is how do we design for the inner loops of the circular economy. And if we look on the right-hand side in blue here, we can see that there's this idea about maintaining and prolonging life, about redistributing and reusing. And it's those things which we see that can have a big effect on composites, on transportation, and how we achieve that could have a big effect on total sustainability and overall life cycle analysis. Recycling is there, and there is also the idea that some of this eventually will fall out of the loop and will have to go to landfill or other uses. But it's really just not just about recycling, it's about how to put all of these things together to give a more sustainable future. And what I'd like to do is to talk about maybe a couple of the aspects of that and how that in circular economy can be impacted. The picture there is a modular chassis which we designed a number of years ago now. It's based around carbon fibre, but using that as an example, we were designing that one, which is something which could be remanufactured easily, and I put down distributed manufacturing there. That is something where rather than making something in one factory, you can spread out the manufacturing, and maybe that also helps to catalyze some of the ideas where you can remanufacture because you're doing this much closer to the end market. And it's also designed for extended use. This is a very similar business model to people like River Simple, for instance. and maybe sort of the leasing model there. And quite often associated with this is not just a change in materials, but a change in business model as well. And so there are these ideas which have been around for maybe a number of years now, and is something which has always felt like it's on the edge of happening. And as I say, we've been involved in this a number of years ago. But what happens quite often is when the OEMs get involved or the vehicle manufacturers get involved, they say, that's not how we build cars. We want to do it something different. So we have this sort of tension, this dilemma or this dichotomy, which we need to sort of find a way around. And maybe that's something which can come out of things like for instance, the Rediscover program, which we've just been hearing about, where we get different groups talking together and we can then all come together to come up with some solutions. Next thing I would say is we always think about when we talk about transportation, and especially with composites, one of the first things that comes to mind is hypercars. We have lots of nice pictures of maybe some McLarens or similar, which are very carbon fiber intensive, composite intensive. And that is an amazing sort of part of the industry, especially as we move into the motorsport industry. The UK has great strength in that area. And that's something which we see and expect to continue over many years. But there's also, we should remember, there's a new type of industry starting to occur. And that's around this personal transportation, personal mobility, whether these pods here, it's a picture I took at Royal Manufacturing Group earlier on this year. And it is maybe some of these areas where we can also start to see the change in sustainability. But to do that, what sort of things do we actually need to have? I think that Lucy in the last presentation talked a little bit about some of the material properties. But if we're going to put a car as of materials into production for transportation, there are some things which has to be needed to be done, whether that's dismantled and recycled. But there's also things like corrosion resistance. And you think, well, that's okay, so composites don't rust, but maybe they suffer from water susceptibility or to other solvents such as brake fluid, or maybe something which is coming out of the motors. So we have to make sure that these things are fit for purpose. And as always, the top line there is productionized at a suitable cost. But it doesn't mean it's necessarily has to be the cheapest, but it has to be at a suitable cost. And one thing I haven't put on that list is strength and stiffness. And so what we're saying here is maybe that's not so important, because although it has to survive in the environment, the ability to have something which is the best structural strength maybe isn't so important if you can get something which works and at a suitable cost. And this is something which we're going to expect to see more about, is the balance of energy, usage, strength and cost is going to come more to the fore. This is a couple of sort of ideas which I could put out there. So this is one from H2X, an Australian company making hydrogen vehicles. And what they've done here is similar to maybe River Simple. What they've done is put the whole sort of ecosystem together that says we're going from fields to hydrogen, and it all sort of stacks up. And so the idea there is, rather than saying, actually, we can make this little bit better, this little bit a little bit better, rather than focusing on, say, how do we improve the properties of this particular natural composite, they put the whole thing together to create a single solution. And again, back to this supply chain idea, but extending that to something which is a complete industry-wide solution, which all stacks up and it all works together. So maybe not just focusing on one particular area, but making something which comes together. And it may be around a single material, bio-based. I'm quite interested in some of the thermoplastic polyesters, PET, PVT as an example. But they are interesting because not in their own right, but how they could form part of this big system. The other part I'd like to talk about is maybe we can use what we already have, but use it in a better way. And what I'd like to do is talk about use natural fibers as an example. We've already heard, and we pretty much already know, that natural fibers have variable properties. But if we go back and have a look at see how these fibers are taken from the field to the end fiber, you'll see that there's a number of processes in there. Some of those are required to allow us to meet maybe moisture absorption requirements. Other of those processes are put in there to help reduce material property variations. But maybe there is a different way of looking at this. Rather than saying we're trying to get to a minimum set of properties or we design with allowables, we embrace that variation and then say, this is a variable material, how do we design with variability? Earlier on this conference, Dr. Pimenta from Imperial was talking about some of the stochastic materials design processes which they've been using for discontinuous fiber composites. We have a number of those as well, which we've been working on using probably similar techniques about how do you design for variable material properties, and other people also been looking at how do you design for variable loads. And maybe that is a sort of slight different way of using this. And maybe that means we can then take out some of these processes which reduce both the cost of the materials, but also the energy burden of some of these environmental materials. But to do that, there are some enabling technologies. Maybe it needs to have some more sensors to understand what we have, but there's also how do you manufacture things which have got variable material properties. Maybe we start need to look at varying the manufacturing processes. And I realise that this is counter-cultural, and it is, for instance, we have spent most of my life and most of my career trying to figure out how you reduce variability, how you make better manufacturing processes. But maybe if we're going to use these sort of materials, we need to turn that around and say, how do we use the materials that we have, but use them in a better way? We've just got the last couple of slides now, so we come towards the end of this. I think what I was trying to do is pull together maybe there's some characteristics of sustainable composites. The first one, which that last point I just made, is making the most of all we already have, and how do we change things to allow us to use those materials rather than trying to get materials to conform to what we want them to do. And I suppose this next one, it may be a slightly more contentious. Maybe we don't need lots and lots of different ideas. We just need one solution which is good enough, and we come together to produce something around that. And the other one around that, this all has to be backed up through proper, rigorous life cycle analysis. There is no point in doing something that says it looks green, but what happens is when you go and focus in on the energy, you're using more energy to create something which is a green composite. That little note of caution there is, I don't think we should be focusing to the point where we say we have the, this one is 1% better than this one. This is taking an understanding of, is this a good solution overall? And then underneath that, right at the beginning, it was talking about things which are driven by legislation and also driven by customer requirements. We must remember that both of those things are going to shape what we're going to be able to put out there. Last slide, put forward here. What does this transportation really look like? So again, we're all aware of that transportation is changing. Is it changing towards modular distributed cars? Is it the pods? And for those who are in the UK, we may be aware that for the first time from this coming Saturday in 2 days' time, these electric scooters are going to be allowed on the road. They're going to be legal for use on the road. And if you start putting various sort of things, different modes of transport into the mix, and understanding how all of these things work together to have something which is sustainable, maybe that's how we start to look to see how we can make a sustainable composite solutions which lead us towards net zero. And I think I'll leave you with that one, and hopefully there's some questions.
Thank you very much, Kevin. That's absolutely brilliant. So yes, we've got one question already come through from John Summerscales. So rather than carrying all the electricities in battery, would it make sense to take it from tram wires to induction loops, albeit with an upfront infrastructure costs, maybe to reduce the vehicle mass?
Thanks, John. That's an interesting question. So there's been a number of studies, as I think you're aware. For instance, there's work going on in Sweden, which has been looking about embedding the wires in motorways to give you induction charging, and that's mostly been used for things such as the heavy freight industry. And it appears that some of the early work in that area, where you're looking at large vehicles which have got sort of high load capacities, such as the semi-trucks, then you start to see a benefit of that. For the smaller vehicles, maybe less so. And if we're looking at the pod solutions, the return to base, where you do trickle charging, for instance, each time it goes there, is a more efficient way of doing that, because you don't, as you say, have the infrastructure costs, but also you don't have to have the sort of extended sort of charging system in place as well. So I could see there will be some areas where that happens, but not in all of them.
Thank you very much. So while I wait for a couple more to come through, how do you see the typically 5-year design cycle for new automotive vehicles changing in light of the need to drive more sustainable transportation? Will it go up for longevity or down to count on the new technologies?
So from a vehicle sales point of view?
Yeah. I think so.
I think that the answer I'd like to give is that it would be for longevity. But most of the vehicle manufacturers at the moment, their accounting practices are very much based upon increasing unit costs, so increasing unit sales, and continuing to develop new product to increase their market share. So with that driving, the consumers driving that at the moment, I don't see that's going to change, and it's going to go in the wrong direction, which is part of our problem if we want to go to a sustainable solution. And I think breaking out of that is going to be key aspect to this. And that's why some of these other business cases which people are looking at, such as the River Simple case or the H2X case in Australia, those are interesting because they're trying to break that business model. And by breaking that business model allows that sustainability.
Thank you very much. So, and one last question from Stella Job. Kevin, what's the optimum material solution for a body in white for a sustainability perspective?
There's many answers to that one, Stella. So I think that it really comes down to how do we get the overall life cycle down. And I think most of that is going to be driven by if we can reduce the end of vehicle life by extending vehicle lives. And I think that's what's going to drive that there. But as Tim's already alluded to do that, we've got to change the way which people consume this product and the way which the vehicle manufacturers sell this product. So from a pure environmental point of view, from a pure materials point of view, having something which is low weight, reduces overall emissions and can be reused is the ideal solution.
Brilliant. Thank you very much. And thank you for a really quite interesting talk. I've learned something. So I'd like to now introduce our final speaker for today. Before we move into a bit of a panel discussion. So this is Professor Kerry Kerwin. Now, I wasn't sure which title to introduce you with first, Kerry. I'm Deputy Pro-Vice Chancellor for the University of Warwick, Trustee of the Alan Turing Institute and a Professor at the Warwick Manufacturing Group, and a whole host more. So I am very excited to be hearing your talk on the potential for sustainable composites. Thank you.
Thank you, Tim. I feel you might be disappointed now. Anyway, yes, thanks. So I was asked to just give some examples of some of the stuff we've been working on at Warwick, and hopefully you can see my screen. It says. Okay, hopefully you can see my screen. So I was asked to give some examples of what we're doing at Warwick, and particularly from within my group. So, I mean, Kevin's kindly put up a couple of pictures of Warwick. We are literally smack bang in the middle of England, about 3 miles geographically from the furthest from the sea as you can possibly get. So I see John's on from down in Plymouth. We don't have a marine aspect of such, but we do a lot of land transport systems. So I thought I'd hang most of the conversation off of that. There's a pretty picture of my office, which I haven't seen for several months. But my group, we essentially do a lot of applied research. So we do have some fundamental stuff going on, but what we do is work a lot with industry, and we're developing a lot of materials and processes that essentially are circular in nature but are tackling real world problems. So we work in diverse areas. So we've got really big areas of battery manufacturing, composites, which I'll concentrate on here, but also water treatment. And by the end of this, hopefully you'll understand actually these things aren't necessarily sort of completely independent. There are some crossover opportunities that we found. So the talk I'm going to talk mainly about is called avoiding the fatberg, which is something that is a problem that our water partners struggle with. If you imagine, vegetable oils are readily used quite a lot in the UK. For making plastics, and they're used in things like PVCs for plasticizers. About 200,000 tons a year are used, but obviously most people use them for cooking, and that creates a massive problem. So if you look at them for the epoxy resins that they're used in, they have bio-based content. It's not economically competitive because vegetable oil is more expensive. It creates issues with the insecurity in the food supply chain, which has been sort of accelerated by the coronavirus. Actually, we've seen lots of shortages of food, and one of the shortages is actually in the vegetable oil production, a lot of which doesn't take place here in the UK. And so what we were looking for was initially with some Brazilian partners, actually some more sustainable and affordable triglyceride sources for the chemical industry. But as I say, the vast majority of this stuff actually we use for cooking, and it ends up down the drains. So anybody at home who's put cooking oil, use cooking oil down the drains, this is what happens underneath your feet. You end up with the fatbergs, and this one is from down in sort of Devon way. It's 64 meters long, this particular fatberg was. And if you go even better, there's one that was found in London. It's 130 tons in weight and about 2 football pitches long. But these things actually comprise lots of interesting materials. So they are fats and they are interesting oils and greases. So we did some work on how we can, the trick is to prevent them going down there in the first place. So you've got to find a way of dealing with these things. So what we were looking at was valorizing waste vegetable oil. And if you imagine, it's not non-edible. By the time it's been finished with, it's not much. It doesn't taste very nice. But as I say, the vast majority of people tip it down the drain. So what we're trying to do is find a way of stopping that to happen by finding a demand for it. So we found that we could get this stuff bulk. People do come around and collect it, and then treat it for various applications. But it's 3 times cheaper than normal vegetable oil. And in taking it out of the sewer system, so preventing it going down the drain, we reduce all those problems that are occurring down there underneath our feet. The problem is, frying vegetable oil is actually a really complex chemical set of actions going on, and if you imagine, it degrades. So we have all sorts of things happening like hydrolysis and thermal oxidation and polymerization going on in front of our very eyes. And that's what this sort of chart shows, all these different, and depending on how hot and how long and what's in it and all that, you end up with very variable feedstock essentially, and something that's got a lot less functionality than normal vegetable, the fresh vegetable has. So that's one of the problems that we had to overcome. Now, a few years ago, we did a lot of work working with biodiesel and looking at second generation fuels. So again, vegetable oils, And we learned a lot about how we could remove the polar compounds and the solid residues and take it back to something that chemically looked very, very clean. So we had a clean source of triglycerides. So in that instance, we were mixing it with methanol and glycerin and making biodiesel, or a form of biodiesel. In this instance, what we were doing is mixing it with other chemicals and catalysts and turning it into an epoxidized vegetable oil. So we started along this path, and what we were looking to do was to essentially, the industry standard is Degiba. Now, Degiba-based epoxies are trying to be phased out. They contain bisphenol A and other unwanted chemicals now. And so what we were looking at is, could we actually start, like we did with diesels, could we start introducing a bio or a waste bio content into a commercial blend? And what you see is here, we started off, we looked at it of different types. So 5%, 10% of fresh vegetable oil, used vegetable oil, and then used but treated vegetable oil. And you can see that, as you might expect, it doesn't perform quite as well when you look at the Young's modulus and of strength and stiffness. But you know, below 15% actually it wasn't too bad. Above 15%, you ended up with a significant drop off, and actually you ended up with crystallization and sort of these rather disparate regions within the composite and the polymer of the two different materials. But we did sort of learn a lot from this, and one of the things we were interested in is whether it would act as a plasticizer and an impact modifier. So what we then carried on looking at was all the different types of variables that could influence our properties. So again, neat oil and waste oil. We looked at different types of hardeners. We looked at the ratio of the hardeners that we used, and we looked at different type of catalysts. And what we found with a very long sort of 3-year piece of work was actually the molar ratio was actually the important bit, not actually the waste or the source of the oil, which is quite nice because it means we can take waste oil, we can treat it, and actually it doesn't have a huge influence upon the final properties of the composite that comes out. It's actually the hardener choice and molar ratio that does. So we moved on a little bit further, and here's the first composite sort of layup picture that we've got. So we took our formulation and we made some flax composites and some glass composites, quite traditionally hand wet layup, cured them off, and then we tested them. And what we found was we did indeed manage to get this plasticizing impact modifying property coming through from the bio-based epoxy. So, and you can see in all instances with the flax fibers and the glass fibers and the molar ratios of 10 and 1 and 14, or you can see the influence changing coming through there. So this was really interesting, and we got different types of failure mechanisms as well, and it gave us a lot of opportunity, because I think it was mentioned earlier on, what we're looking at here was, could we exploit some unique properties for certain applications? Didn't necessarily need the best properties overall, but what we needed was some unique ones. And that gave us the opportunity to look at some fracture-based applications, so impact-resistant applications. We also work with recycled carbon fibre, and what's happened there is we've done a lot of work working with ELG, looking at their recovery processes and turning the waste carbon fibre back into useful recycled carbon fibre of different types, whether it be film, whether it be mats or woven pre-pregs and things like that. And what we did here was we thought we combined the two pieces of work. So we took our waste vegetable oil based Degiba mix and added it and used it with recycled carbon fibre and virgin carbon fibre to see what the interesting properties we could come out with. So Carbiso is an off-the-shelf product now. You can buy that. It's a non-woven. It's 100 GSM needle felt mat sort of thing, and also the virgin carbon fibre, which is the industry standard Sigma text there. And you'll notice that the grams per square metre are a lot higher in that, and that's important when we come on a bit later on another slide. But essentially, we made some very nice composites, and when you start testing them, what we again found was, as you might imagine, we would get the strength and the stiffness wasn't as good for the blended ones, but actually the impact performance was better. And also what we also found was our blended, when you do traditional composites approach, which is to look at the specific properties, we actually found our bio-based Degiba recycled carbon fiber composites perform very, very well compared to virgin carbon fiber. So that was an interesting thing. And what we then did was allowed us to go on, and this is something we're working on right now, and that is that this is the Coventry Very Light Railway System. So these parts, I had hoped to have actual pictures of them. So we've gone all the way from the sewers and stopped the stuff going down there and done enough work to turn this into a real world component. And this is the mock-up of them. The parts are being made at the moment. They should have been with us, but due to coronavirus and shutdown, it hasn't been possible. But they are actually, I believe, being manufactured this week to come up for real in-world situ testing. And you can see they're not structural parts, they are actually impact resistant parts of what we're looking at. These are sort of the entry pieces, parts of the vehicle. And they're subject to quite a lot of sort of things hit them at the side. And so impact properties is more important than strength. So then there's a monocoque system inside that provides the strength and structural stiffness. So these are real world parts we're working with, and hopefully you will see these running around the streets of Coventry in the not too distant future. So that was the first project. And the other project I was going to talk to you about briefly was something called EcoBulk, which is another circular economy project that we are involved with, where we take waste and end-of-life products from the automotive, the furniture and the construction sectors. And what we do is we turn them back into products either within or between those sectors. It's quite a big project, 38 different partners across about 12 different countries, several million euros. And what we're actually doing, as I say, is trying to get real circularity with some of these composite materials. So within the automotive one, again, we've got some recycled carbon fiber and the bio-based composites I just spoke about there. We're using them, and we're making trims and fascias and under the hood parts. And there's some specific models that you can see down the bottom there, where this is being put into limited volume sort of test run production lines. So Fiat, one example, and they're again performing very, very well in situ, and we hope they will become standard issue over the next few years. And the other interesting one is furniture. These are all real parts. These are parts that are taken from either from the construction industry or from the wood industry within the wood sector within the furniture industry. And what they've done is essentially being extruded, so wood plastic composite, and we're starting to make sort of, as you can see, various different components out of it: beds, chairs, tables, shelves, that sort of thing. We're actually fitting out conference parks and offices around the campus, and getting real well feedback on these at the moment. And we're finding that people are very interested in them. Companies are very interested, and they actually want to hire the eco room to hold their meetings. So we're getting real well feedback, trying to understand the durability of it. We know the theoretical behaviors of these materials in terms of their sort of fire performance, their number of times you could put them together and take them apart under controlled conditions. But we've now got enough confidence to actually release them into the real world and let them be used and abused and subjected to sort of behaviors that we may not have thought about, people sitting on them and things like that. And so that's another interesting use of sustainable composites. And then the final one that we're involved in on this is the second life, and this is always a problematic one: glass fiber composites from wind turbines. Very, very difficult, and we're looking at what we can do with them. And what we've been doing again is again at Warwick with our European partners, we've managed to turn them into extrusion. So the glass fiber composites being used as a sort of filler material within extrusion. And again, we're making outdoor structures, and as you can see, they're quite pretty for what is normally recycled composites can tend to be quite ugly and chunky. We actually are making quite nice looking structures, which have been designed for aesthetics, and again, they are finding great favour with people. So this is one that's sitting outside within a green area within the woods as a bit of an outdoor gathering or networking area. And we've also got some that are going into our plaza and the art centre as well, again, for people to actually use these things in real life, tell us what they think of them, tell us what they think about the look, the feel, how they interact with them and things like that. So we've got another 2 or 3 years on that work before we're able to bring these things commercially, but as you can see, we're quite high up the TRL levels in terms of getting these things into the market. So the only other one I wanted to just briefly touch upon, 10 years ago, we did something called World First, which was a racing car where we took all the natural materials and recycled materials and say the biodiesels, the lubricants and things like that, and took them into one of the most extreme environments, which was the Formula 3 racing car. Now that car is still running, and actually at the moment is at Silverstone having its mechanics refitted out, because the bits that are broken on it are actually not the green sustainable bits, the more traditional metal components. So it's being refurbished. But what we're also doing is going to relaunch this with lots of these new technologies we've been working on actually onboarded again and taking them to very extreme environments. So incredibly hot, incredibly fast, lots of impact and things like that. And so hopefully in 2021, if you're ever at Silverstone, please come and have a look and see how it's performing. So that was very much a whistle-stop tour. I'll stop sharing there and be interesting to hear people's comments and thoughts.
Thank you. And no, you haven't disappointed. It's actually been very insightful and interesting. So just going back to two of the things you mentioned the eco bulk work of natural and biocomposites, and also end of life examples. How are you bringing the two together?
Sorry, you broke up there and I heard eco bulk.
Sorry. So you had some good examples from the eco bulk work, and also some good examples of where you've designed and manufactured structures out of end of life components. Are you doing any work to bring these two concepts together?
So the automotive piece in the eco bulk, that is using end of life, that's using recycled carbon fibers and some bio-based resins to make new parts, interior parts in cars. Mainly decorative, I have to admit, and certainly a lot of work we've done in automotive with our recycled materials and the bio-based resin is mainly decorative at the minute. I mean, the automotive industry is a very hard industry to get these sort of parts into critical applications, simply for various reasons, safety, long-term commitments to existing designs and supply and things like that. But we are getting there. Very often, I mean, again, perhaps Kevin touched upon this, but some of these materials stand a better chance in new platforms and new vehicles and new applications where you aren't necessarily held back by tradition. That was part of the reason we did the F3 car all those years ago, is we just could not get this stuff into the automotive sector because it was a chicken and egg. We couldn't prove it, and we couldn't get it in because we couldn't prove it. So the Formula 3 approach gave us a great opportunity to go well beyond the performance criteria of automotive and show these things worked.
Interesting. So just a similar question just on the eco bulk work from Stella Job. Do you know how the extrusions from eco bulk compare in terms of cost with similar available products?
My gut feeling at the minute, and we don't know this is a volume issue. At the moment, I suspect they will be more expensive, but we're still proving out performance. So if you imagine, they are still over-engineered. We are still using larger volumes of material than what we need to use for safety reasons. Some of they look quite pretty, the shelters and that, but they are, I can tell you, quite robust. Hurricane proof, I think, was the best description, because they weigh a lot at the minute. So that optimization hasn't gone on yet. We're still working on that. My gut feeling is at the minute they would still be more expensive, but as more of these turbines come down and more of this material comes online and demand grows, then we should hopefully see some economies of scale kicking in.
So I'm going to pick that one up with a question from Dominic Hopwood. He's interested to understand how the fat-derived epoxy resin you discussed could be scaled up.
So there are companies that go around collecting this stuff, and I mean, that all came, we essentially work with the university suppliers, or not suppliers, but recoverers, to take the collections. The chemistry is not that challenging. The scale up isn't that challenging. It's more the cleaning. And as I say, we did it with biodiesel. So what we learned from how to get the oils into a useful form, remove some of those impurities and particulates, and increase a bit of functionality or enhance some functionality. It's scalable. I mean, we could do it the hundreds of litres. We've just never gone beyond that. So in theory, you could scale that up quite easily. And that's your backbone for the polymer.
Cool. Thank you. The next one up that's been upvoted is what range of temperature was used to during testing to conclude that the performance was superior to DGEBA systems?
DGEBA. That was done at room temperature. We didn't. I don't think we went up and down the different temperature scales. I mean, that's a 4-year piece of work, so I don't have all of the bits to scale to hand. The papers are on the slide, so the exact details of the test characteristics would be in those papers.
Cool. Thank you. So just for the audience, so we will be sharing what we can of any of the slides where the presenters have let us, and don't forget this is recorded. So if you did want to go back and have a quick peek at that, then you can. A couple more questions before I moved on to the panel. So one of the problems with bioresin is that mechanical properties can be lower than synthetic resin. Is it possible to change the synthetics resins within some of these structural applications? What would you see the challenges with trying to convince and make a change?
So that's the piece of work that I just showed, that you're absolutely right. Strength and stiffness, the bio-based stuff does not perform anywhere near as well as the synthetic stuff. You can blend, and you'll get, as is quite common, as I say, with fuels and things like that, you can blend these down with polymers as well. Speaking of that, you can blend it, but at a certain point you will get a massive drop off in properties. I think it was about 15% on R1. Below that, there was all sorts of problems, or above that we ended up with all sorts of problems. But what we then look for is unique properties. So as I say, we knew it was a plasticizer, and we knew, or we thought, you would have impact modification properties as a result of that. And so we went for applications where actually modified impact was more desirable than strength and stiffness. And that's probably the best way to use it in a minute, is to say, how can you differentiate it? Don't try and compete directly. We've done a good job over the last 50 years optimizing these other materials. Let's look for some unique opportunities for these bio-based things.
Actually, some quite good advice. I might have to think about that myself. Thank you. So if we can move to the panel discussions, but just in the interest of time, what I'd really like, if the other panelists could turn their cameras and microphones on, just to quickly introduce tomorrow, for anybody who has a particular time cutoff. We've got some amazing speakers, and it's the last day of the event. We have Nadeem Zahawi, who's the MP Minister for Business and Industry, Richard Oldfield, Chief Executive of the National Composites Centre, and Jane Nicholson, who's the Director for Research Base at the EPSRC. So please do join tomorrow, because that also looks to be an exciting event. So we'll move on to the panel discussion, and whilst we get some more general questions in, just to kick off, and this is open to the floor, there's been a lot of interest in the chat about networks. What do you perceive as being the biggest gap in composite sustainability, and how might we build the academic capability to respond? So that's for any of you, if you can.
Sorry, Tim, again, I lost the first half of that sentence.
Oh, I'm sorry.
Okay.
No,
I think it's my connection, I think.
Let me try again. So what do you perceive as being the biggest gap in composite sustainability, and how might we build the academic capability to respond?
So if I can have a go at that, biggest gap for practical use of sustainable composites is probably those design engineering understandings that used so regularly with normal composites. Without them, we struggle to get engineers to use them, and therefore the demand is not necessarily what it could be for them. That's certainly where we spend most of our time working to give those design comforts and engineering data so that it can be used practically. And it's very hard because of the variability inherent within the materials. So that's where I think the biggest gap lies in inhibiting their real world adoption anyway.
Kevin, Lucy, anything to add?
I'd say I echo what Kerry was saying. I think a lot of the hesitation that we see when considering sustainable alternatives is that often people are reluctant to take them up in particular in commercial applications, because there's a bit of a lack of trust in some instances as to their performance. So coupled with that, I think what can we do in academic circles to sort of stimulate that is largely about education for me. I think we've got a generation of students coming through are more sustainably motivated, or are more sustainably motivated than ever before. And we really need to capitalise on that and make them aware of the potential of composites to solve some of the issues that they notice, and encourage them into an industry that can have a real impact on that.
Anything, Kevin?
I think I'm in a similar vein to some of the things which Kerry's been speaking about there. As we talked about, it's not just focusing on sort of raw material properties, but it's that balance of sort of energy usage, cost, and how do you get them into a design. So you've got to have all of those things in place. And if you just focus on one thing, it just doesn't work. And I think the other part about us, what we talked about earlier, and Kerry and Lucy also mentioned, is having a couple of wins, a couple of things out there which you've just used to show that it can be done. And I know when we first started looking at, for instance, the carbon fibre vehicle structures, just making some structures and showing that they could be used for cars was the major sort of step, and that's helped catalyse some of that work as well.
Cool. Thank you. So sorry, excuse me, I'll just try and read. There's been a lot of questions suddenly come through. Do you feel there is the collective level of political initiatives and legislation to drive sustainability? That's from Ian Bevis.
I'll start on this one. I think there is a growing political desire to really achieve net zero. That does feel like it's something which is real and tangible, and something which is driving thinking. But balanced along that is how it affects the economics, how it affects the costs. And I think it's skimmed past that a bit, but that is one of our real sort of continued struggles over the sort of many years previous to this. And that's going to be the one which is going forward, is how do we break out of that cost barrier while it's still seen as a costly alternative. However much will there is, I don't think it's going to really drive it through. So I think that's a sort of legislation helps, but it's not the final answer.
Yeah, I think the net zero target gives a bit more focus to all of industry that maybe hasn't necessarily been there before. It's good to have a target, and it's good to have something that is very, very measurable. So that legislation is pointing us in the right direction, and some industries are further ahead than others in terms of more specific requirements. But I think there's definitely more that's needed, because as Kevin was saying, a lot of the time when it comes down to commercial uptake, it comes down to the business case and the costs associated, and there needs to sometimes be like an additional nudge to head people in the right direction in terms of sustainability, I think.
Well, just let's move on to another one that's come up a couple of times around waste and particularly in production and making application. Have you any ideas about the recycling or reuse of some of the consumables within these manufacturing processes?
In terms, okay, so you mean things like sort of tapes and layups and things like that?
Yeah, vacuum consumables, some of the wasted. Are there any emerging technologies that might help, or potentially about the actual recycling of the consumables themselves?
So I'm aware of some. I mean, these tend to fall into general chemical cracking or polymer cracking approaches. So those sort of mixed materials, because that is inherently what they are, it's going to be a mixed polymer waste stream. There are emergent techniques appearing and at sort of pilot scale that can cope with these things. I'll be absolutely honest with you, I think a lot of, I mean, in-house scrap can be dealt with relatively simply by manufacturing processes. They can reintroduce some of it back into the process, limited volume, or they can have a controlled collection system. It's really what happens once those things have been collected. Where do they go, and what happens to them? So it's not particularly joined up, I don't think. There's also all sorts of issues with certification and things like that, where the materials come from and where they can then be used again. Certainly we've had conversations with the aerospace industry and things like that, where actually they can't even take their own scrap materials, recycle and reuse them, because they're just not allowed to. So there are some legislative barriers about that kind of activity.
It's very interesting. So would you ever see a future where we've got some kind of national collection feeding in the right kind of volumes?
I think you're probably, I mean, it's a really good question, because I don't actually know the answer. I think it's more likely that each manufacturer will probably take their own route. Bearing in mind, you're going to have a huge diversity even within a manufacturing plant. You can have a huge diversity of materials coming out. As to whether you'd ever have a national vac bag recycling centre, I honestly don't know.
I think this is something which we've looked into, not from a research point of view, but from an end user point of view. And somebody upstairs from here may disagree with me, but we haven't really found a suitable answer to that yet. So at the moment, they all go into various forms of the waste stream. I suppose the underlying answer to this is we shouldn't be using them anyway. We need to change. We need to find automated or systems which don't use those consumables, and that's the final answer. But I realise that that's not going to answer our current problem of what we have coming out of our various factories today. So.
I'd say that there's quite a lot of relevant research being undertaken at CPI at the moment in terms of challenging plastic waste. So although perhaps not looking at this specific avenue at the moment, it's definitely something that's been raised time and time again by a number of different customers and members of our network. And I think it is something that needs a near-term solution, and then let's look to the future as Kevin's suggesting. But hopefully different programs such as what's going on at CPI and other organisations as well can help.
Thank you. So just in the interest of time, I'm going to ask one last question before wrapping up. What do you see as being the emerging changes that might disrupt the composite industry?
That's a big question.
It is. I thought about asking the pot of gold again, but
I'll have a go first. Give me a bit more time. So, I think the main ones really are going to be this focus on net zero, and that is, as we get closer towards that is going to just start focusing more and more people's minds and trying to understand what that really means on a day-to-day basis. We've been in a situation, I suppose, more recently where effectively things have just stopped happening, and it's that sort of level of non-activity we need to get to to get towards net zero. So I think it shows it really is that which is going to drive more and more thinking. And assuming the governments continue to stand by it, for want of a better word, and consuming, that's going to continue to drive consumer behaviour, then that's going to be both the sort of biggest challenge and the biggest opportunity.
I'd say a big challenge, though, that the composites industry might face in the future is as the general consumers are becoming more and more aware of sustainability issues and problems and are becoming more sustainably minded. There's a bit of an embargo on plastics at the moment. Everyone hates plastics, and although there's a time and a place for them, there's a bit of a negative connotation around them at the moment within the general public. And I think something that could be at risk to the composites industry is the fact that currently we're not really considered to be plastics, although it is part of it. And we don't really see that reputation or that negative connotation associated with it. And I think that there is the potential for that to be a risk to further growth of the composites industry, that sort of blacklisting of composites because they're plastics.
So I'm going to ask Kerry, have you got how could we as a community try and perhaps educate on where composite, the truth behind it, and actually the potential that they really do show, without having the wrong direction that Lucy warned about?
So I mean, Lucy's right. You'll be amazed at how many project proposals that you see that have been coming in for government funding. Plastics and composites are bad. We need to get plastics out of the system and things like that. I mean, the only thing is this COVID situation perversely has completely reversed that. Plastics usage is going through the roof, and it probably will be for the foreseeable, which is completely going against where we were before. It is about informing correctly. I mean, I spent a couple of evenings down in Parliament before lockdown making just that point. Plastics themselves and composites are wonderful materials that need to be used in the right applications, in the right areas. The problem is we tend to use them where they shouldn't be used at the minute for various reasons. But if we are going to make that sort of zero carbon approach, if we are going to realise our electric vehicle and the electric vehicle revolution and things like that, they are going to have composites are going to play a massive role in it. So it is about educating policymakers. It is about educating the public. The other thing to be aware of is, of course, is the competing industries. So your glass industries, your metal industries, they're not standing still. They are doing much lighter, stronger, stiffer, impact resistant variants as well. And so it's quite a complex. I mean, it's this merry-go-round constantly between the different materials choices. But at the minute, I think education is going to be the key thing to prevent composite sliding down the pecking order.
Thank you very much, everybody. So thank you, Kerry, Lucy, Kevin, and Alan from Vestas earlier on. Just before we completely wrap up, I look forward to seeing everybody rejoin tomorrow. Just as a reminder, we've got a really interesting workshop and some more talks from Nadeem Zahawi, Richard Oldfield, and Jane Nicholson. So look forward to seeing you back and hearing some more of your great questions. Thank you.